Welcome to section 1.5, parent functions and transformations, and also piecewise functions. So to start today, we're going to look at a couple basic parent functions that we definitely need to know before we can transform them. So what is a parent function? A parent function is the simplest of the functions in a family. This is the function that is transformed to create other members in a family of functions. And like I said, we're going to look at a couple of very basic ones that you pretty much have to memorize moving forward. So to start here, we look at the constant function. So f of x is equal to some number c, where c is any real number. I just randomly chose 3. It could be any real number, but we chose 3. So what does that mean? Whatever x value you put in, you get 3 back. Here's a picture of that graph. Its domain is all real numbers. There is no restriction on that domain. And the range is only the c value. That's it. So you just put bracket c. So in this case, it'd be bracket 3. Next function is the linear function. F of x equals x. So basically whatever you put in, you get back. So there's a couple examples of points. You can see the graph of that. Once again, domain is all real numbers. There's no restrictions on the domain. And also, the range is all real numbers because it'll go down forever and up forever. Third one is the quadratic function. So whatever you put in, you square it and you get back. Here's a couple points that we've plotted. Once again, domain, all real numbers. There are no restrictions on the domain. There's nothing I can't put into that function. The range, it does stop at 0. Okay, so it does hit 0. So we'll start at 0 with a bracket, and that will go to infinity. The fourth one's a cubic function. So whatever you put in a cube, here's a couple example points. Once again, no restrictions in our domain. And it will go up and down forever, so no restrictions on our range. Fifth one is a square root function. So whatever you put in, you take the square root of that. Here's an example of that. This is the first time it does have a restriction on the domain. Remember that we have to take only square roots of positives or zeros. So our domain here would be 0 to infinity. And looking at the graph, the range is also 0 to infinity. Starts at y equals 0 and will go up forever. The absolute value function, remember absolute value is a distance from 0. So whatever you put in, the positive value of that is your output. There are no restrictions on the domain for that. And looking at the graph, the range starts at 0 and goes to infinity. And the last one we definitely know is the reciprocal function. Basically what it means, whatever you put in, you're going to take the reciprocal of that. So for example, if you put in -2, the reciprocal of that is -1/2. Now you can see, because we have an x in the denominator, we can't put 0 in the denominator. So the domain is everything but 0. Remember to write that. Negative infinity to 0, union 0 to infinity. And in this case, the range is the same thing because we can't use y equals 0 as well. So negative infinity to 0, union 0 to infinity. They usually won't be the same domain and range for this one, but if there's no transformations on it, they're both the same. So those 7 functions are functions you need to know and be able to recognize as we go through the rest of this section. So now what we're going to do, we're going to transform these. Transformations of a parent function can change the position and or the shape of a parent graph. So we're going to start with translations, which are also called shifts. Now, I want you to say translation, but generally people think of it as a shift. Shift right, shift down, whatever. Okay? You're also going to hear me say a lot inside or outside of the function. So in this example, plus d is outside of the function. So that immediately tells us it's a transformation to the y coordinates. It's a vertical transformation of some sort. minus c is inside the function. So that tells me it's a horizontal transformation of some sort. Okay? Because we're adding or subtracting, those are translations. Whenever you add or subtract something to a function, those are translations or shifts. So if it's outside the function, it's a vertical translation, and that will basically move the graph up or down. If it's plus d, it's up. If it's minus d, it's down. The second one, we have f of x minus c. Again, since that's inside the function, it's a horizontal translation. That's going to move the graph left or right. It's the opposite of that, though. So if you see x minus c, you might be thinking that moves left because it's negative, but it's actually the opposite of that. So x minus c will move it to the right, and x plus c will move it to the left. So let's take a look at a couple examples. First, let's graph the parent function. Again, this is just, you have to know what the parent function looks like for the absolute value graph. So I know the absolute value graph is a v that doesn't want to graph. So there's my absolute value parent function. Remember, this is called the parent function. And the first one here, think to yourself, is 1 inside or outside of the function? The function is the absolute value. So the 1 is inside the function. So that immediately tells me this is going to be a horizontal shift or translation. Okay, then you got to think, is it left or right? Since it's plus 1, that means we're going to move it to the left. So I say horizontal translation, left, 1. So basically what we're going to do is we're going to subtract 1 from all of our x coordinates over here. Okay? So for example, this point right here is negative 2, 2. If you subtract 1 from the x coordinate, you get negative 3, 2. This point is obviously 0, 0. If we subtract 1 from the x coordinate, we get negative 1, 0. And let's go this point right here. I'm just picking random points. This is 3, 3. Subtract 1 from there, we get, from the x coordinate, we get 2, 3. Connect dots. And there's our shift to the left, 1. The third one, this is outside the function, so you immediately are thinking this is a vertical translation. And since it's minus, we're going to go down 1, which means we're going to subtract 1 from the y coordinates. So, back to our parent. Negative 2, 2, subtracting 1 from the y coordinate is negative 2, 1. Zero, 0, subtracting 1 from the y coordinate is 0, negative 1. And 3, 3, subtracting 1, we get 3, 2. Okay, and then connect those. And there's our translated vertically down 1 graph. The last one is 2 transformations. This one is inside the function, so I know that's going to be horizontal. And since it's negative, that's going to move to the right 2. This one's outside the function, so I know that is vertical. And since it's plus, it's going to be up 3. So we're going to take our original points, we're going to add 2 to the x coordinates and and add 3 to the y coordinate. So negative 2, 2, add 2 to y, add 2 to x, and add 3 to y, we get 0, 5. And then 0, 0, add 2 to x, add 3 to y. We get 2, 3. And then 3, 3, add 2 to x, add 3 to y, we get 5, 6. So again, here's our double translated absolute value graph. Now we're going to look at dilations. Dilations are going to make the graphs thinner or wider. And what I want you to know is that vertical compressions and horizontal stretches basically look the same. And vertical stretches and horizontal compressions look the same. So I always tell my students, just get everything to be vertical, and it makes it a whole lot easier if you can. Okay? So what do a vertical compression and horizontal stretch look like? They both make the graph wider. How do I know if it's a vertical compression or a horizontal stretch? If A outside the function is multiplying and it's between 0 and 1. Or if B inside the function is between 0 and 1. And then for vertical stretch or horizontal compression, those again look the same. How do I know if it's that? Well, if it's A outside the function multiplying and it's bigger than 1, or if it's B inside the function multiplying and it's bigger than 1. Okay, basically what we'll do then is we're going to multiply the y coordinates or the x coordinates by A or B. Okay, if you want to pause the video to write all that stuff down, please feel free to do that. It says multiply y coordinates by A or multiply x coordinates by B before the function. So when you do, that's why I always suggest making it vertical. It's a lot easier if you can change it to vertical, which we're going to see an example here very shortly. All right, so here's my parent function, y equals x squared. I know what that looks like. And here's 5 points. So 2x squared, the 2 is outside the function. It's not, the 2 is not being squared, so it's outside the function. It's bigger than 1, so I know this is a vertical stretch. Vertical stretch. And what we say is we call it a scale factor. So we say by scale factor 2. So what we're going to do is we're going to take all the y coordinates and multiply them by 2. So for example, negative 1, 1, we'll go to negative 1, 2. 0, 0 stays at 0, 0. And 1, 1, we'll go to 1, 2. And you can see how the graph is becoming much thinner. Okay, next one we have 1/2 outside the function. So again, it's vertical. But this time, it's going to be a vertical compression because that number out in front is between 0 and 1. So it's a vertical compression by scale factor of 1/2. So take the y coordinates and multiply by 1/2. So negative 1, 1 will go to negative 1, 1/2. 0, 0 stays at 0, 0. And 1, 1 will go to 1, 1/2. Okay, and then for further clarification, the point negative 2, 4, multiplying 4 by 1/2, we'll go to negative 2, 2. And same thing at 2, 2. So you can see now how this becomes much wider than the original graph. Okay, this next one here, this is horizontal. Okay, we can tell because it's inside the function. Okay, and since it's bigger than 1, it's a horizontal compression. But again, I want you to think of this as the same thing as a vertical stretch. Because if we were to multiply that out, we would get 4x squared. And now it's the same thing as a vertical stretch. Okay, so negative 1, 1 will go to negative 1, 4. 0, 0 stays at 0, 0. And 1, 1 will go to 1, 4. And now you can see exactly how skinny that graph is compared to the original parent function. Same thing here. If we multiply this out, we would get 1/4 x squared. Okay, technically, again, that 1/2 being inside the function, that is horizontal. It'd be a horizontal stretch. But now we can look at it and we can say, all right, I just know that it's going to be it's going to look like a vertical compression. Okay, so negative 2, 4 is going to go to negative 2, 1 because we're basically multiplying the y coordinates by 4. 0, 0 stays at 0, 0, and then 2, 4 will go to 2, 1. And you can see how wide that graph is compared to the original. Okay, the last one is reflections, before we take a look at a couple examples. So reflection is basically going to flip the graph over some type of axis. Okay, a vertical reflection flips the graph up or down. We're going to multiply the y coordinates by -1. Horizontal reflection reflects the graph horizontally, flips the graph left or right, and multiply the x coordinates by -1. Again, if you want to pause the video to write that down, go for it. We're going to look at the square root function. So I know what that looks like. I know 0, 0, 1, 1, and 4, 2. All right, this first one here is outside the function, so that is a vertical reflection. Which means we're going to multiply all the y coordinates by -1. So 0, 0 stays at 0, 0. 1, 1 now goes to 1, -1. And 4, 2 goes to 4, -2. The last one here, this is inside the function, so it's a horizontal reflection. So I'm going to multiply all the x coordinates by -1. So 0, 0 stays at 0, 0. 1, 1 goes to -1, 1. And then 4, 2 goes to -4, 2.